Good afternoon. Thank you very much. It's a pleasure for me to be here. And I would like to share with you my interest in this subject, the idea of having, say, qubits and to have them to send around. So we have to start from something, and I would like to start from a wave. I wonder if you ever seen such a wave, this particular with the stars here. It's the wave that was chosen to represent, say, a movement that, say, collected about 3,000 scientists, a bit more than that, that signed, we signed in 2016 a manifesto proposing to the European community the start of a program for exploiting the quantum mechanics applied to technology. So you see, it's a different cut with respect to just a theory that is used to understand nature, and we shall use the next hour just to elaborate on this. Okay. So at the end, this manifesto was actually received, and a program that was called a flagship program by the European Union started. You can see the photograph of the start, the official start last year, and is based, is pictured like a temple, is based on the application of quantum technologies. We shall learn what they are on different pillars like communication, simulation, sensor, and computing. It's based on education, so essentially, science and engineering, okay, and it will support essentially the progress of the nations of Europe, in particular energy, health, and security. Okay, it has a 10-year program. It is, say, fueled by €1 billion to start with, okay, plus several contributions, sometimes a significant contribution from countries, okay, for particular countries. And it has a development plan that goes even beyond the 10 years, okay, including, say, development of better clocks, better sensor, quantum links, we shall talk about that, quantum simulation, quantum computing, things like that. There are things that probably you have heard about this week, okay? So what's our topic here? So you see, we started from, say, a perspective of application. So we have to go a bit, say, back to the basic, okay, to understand which part is essential for this technology, for this set of technologies, okay, and how this can be used. And I have a demonstration here for you to show also live, hopefully, what is going to be. So, a fundamental memento for the birth of quantum physics is just something as simple as the spectrum of a lamp, of a metal lamp, okay, cadmium in this case, okay? You have lines. Well, you see, what's bad with this? Okay, you actually have a vapor, you have a discharge, you have some power supply, and then you get lines. If you have a prisma, a Newton prisma, get them dispersed, they come with the nice colors, okay? You change the vapor, you change the color. Yeah, with the problem that this was not something that classical physics could actually say, explain. So there was no comprehension of this phenomena of the discrete line within the electromagnetic theory of Maxwell. And so, well, everything was on hold until 2013 when we have Niels Bohr that, explain the known experiment, okay, with, say, a theory for which you have essentially these quantized levels. So in synthesis, atoms, which were realized there that were actually existing, are not objects that can be described by the law of Maxwell alone. Okay, I mean, Maxwell law are, of course, very good for some phenomena, but it's not the whole story. Energy level cannot have any value, okay, but only some values, okay. Electrons are in state with a fixed energy, let's say, but they can change state, and such a transition occur with specific energy, energy quanta for that is to be, say, absorbed or released. Okay, and this was a paramount change, okay, in understanding, and that was for the matter, and same came from another revolution, came from the radiation. Okay, so Einstein, in order to interpret a few phenomena, the most important of which is the photoelectric effect, which was again something that was not understood with the law of Maxwell, but at the same time is, say, quite diffuse, and in particular the use of your very camera in the phone, okay, for instance, is actually based on this absorption of discrete quantum of energy, put forward in this paper a statement with his traditional lightness, but at the same time with his vision that was really visionary and revolutionary, according to the assumption that, say, is based on the experiment. The energy is essentially not continuously distributed over ever-increasing volume, but it consists of a finite number of energy quanta localized in space, which move without being divided and which can be absorbed or emitted only as a wall. This is the word of Einstein, and indeed this is proven true, okay? And he got actually the Nobel Prize for this, not for relativity, because this actually the solution of a very hard problem, okay? So let's see a bit what this means, okay? Light coming in grains, okay? We are very much accustomed to have light as waves, okay? We have seen the waves before, and diffraction and interference are classical subjects for say, supporting this vision of light as a wave. But let's walk for a moment in this different direction. Let's talk about grains. Okay, so let's say if we have both wave and particle, okay, and the particles are good because they solve the problem of the black body and the photoelectric effect. Okay, they demonstrate with the theory started from Einstein that actually photon the quantum state of the radiation. Okay, so to us, what could be say? What can we say? Understand when we talk light is grainy? Well, what about grainy things? Okay, so if light is grainy, how do photons reach us? Okay, so for instance, how can I sort out things that have different type of grains? Okay, so question is any types? Okay, any suggestion? Well, if it's actually any type of grains, let's talk about something we do have in our kitchen, and so we can talk about this. So I've made a little experiment for you, okay, at home. This is my kitchen table, and this is a jar in which I pour cornflakes, rice. This is couscous, and these are the famous rigatoni, which I presume you have to try before leaving Italy for sure. So you have to guess, okay, which is which by hearing the recording that they are doing. Now I'm trying this. Okay. So number one. Can you hear it? Three. Well, that was easy. Huh? And number four. So, and couscous? Okay. Well, it's actually rigatoni, eh? You have to be careful with that. Okay, why this? Well, very good. So when we take light of different types, okay, one type is the laser light I'm using right now. I have it a laser in my hand, okay, and the other is thermal light. I mean, it could be the sun, or even it could be a fire. It could be a lamp, okay, a standard lamp. You can discriminate these two things. This is just sunlight, and this is a photo I took in an experiment on quantum communication from the island on Tenerife to the island for a beam that was traveling 140 kilometers to the island of La Palma. Okay, so what's the point here? Well, the point is that if we listen at the grainy thermal light, is this. Oh, sorry. It has a pattern, okay? And you have to compare this pattern with the other one. Can you tell the difference? It lacks of burst and it lacks of silences, okay? And the reason is that a laser is a wonderful example of something that is actually a collective emission in a resonator. So it's as if there were a director that, say, pays the orchestra to emit, okay? While the sun, for instance, or a lamp, is actually a collection of many atoms that they decide when to emit and where to emit independently, okay? And so you may have such a burst in the case of a thermal light, but not much in the light of the laser. And this light is called thermal, and that light is called coherent. And indeed, you can, say, derive the distribution of such events that they have, say, fancy name, Poissonian distribution, again, the coherent light, and Bose-Einstein again, in the case of the thermal one, okay? But so it's actually the graininess. So you see, these are examples for which the light could be at the same power, the same, say, frequency, okay? But still, if you look at the core, so the, say, statistics, let's say how the grain arrive, you can, say, devise, you can understand what is the origin of the light itself. Okay? So now let's see what's the relationship with the matter is. I think you have seen or imagined this a number of times. Look at this moment, okay? You have the orbit, the simplified orbit of Bohr, okay? By the absorption of some energy, you are forced to change the orbit, but as the electron is then moved to a more external orbit, of course the electron is pulled toward the nucleus because you have the electric force that it's pulling, so sooner or later he will return to the lower orbit, so the orbit is unstable. And it does so by emitting, say, the energy they received. Such energy is emitted with a photon. So if you want to take these things a bit in general, let's look at this. Okay, on one side, I depicted the two energy level of the atoms. So, for instance, when the atom has absorbed the energy, we can show it a bit like there. Okay, I don't know, like two branch, and you have a bird sitting on the higher branch, and then it can go down, but at the same time, you release the energy. So if this is instead the mode of the light, initially the mode was empty, and when the energy has been released, you have that the light possesses an energy corresponding to the one released by the atom. Okay, so if you elaborate a bit further, okay, if you say consider in the act, so for a moment imagine to stop in between, okay? What happened? Well, you have that the levels of the atom, okay, are to be described in a way that the electron is no longer here, not even here. So what happens? Well, the quantum mechanics as an explanation for this, as a description for this, by saying that in this moment of the emission, the atom is in superposition of two, say, orthogonal possibilities, okay? One possibility is having the electron in the upper state, the other possibility is having in the lower state, okay? It's like, say, being vertical or being horizontal, okay? They are alternatives, okay? But in this moment, during the process, essentially you have both, okay? You have both, and the interpretation is what? Well, you have a probability of being in one and a probability in being in the other. And as the, say, upper level, as we see, is not there for a long time because it's unstable, such a probability is time-dependent. Okay, time-dependent means that at the beginning it's quite large, okay, and then it goes down to zero, okay? And vice versa, the other one that sums to one, okay, it grows, okay? So this is a situation in which you can understand that quantum mechanics has these things that are, say, orthogonal possibilities, okay, present at the same time, okay? This is something that is, as we call it, non-classical, okay? Why? Because if you take a bit that is stored in one computer, like this one, or a phone or so, whatever, okay, a USB pen, well, you rather don't like that one bit in your memory cell could be either 1 or 0, okay? You actually have paid for a good USB pen in order to have the bit that once set to 1, stay 1, okay? Or set to 0, stay 0, okay? Such a thing of superposition is definitely non-classical, okay? But quantum mechanics brought it inside when it has to describe the microcosmos, so the atoms, the molecules, and things like that. And there is no way around about it. And so, well, the idea is that we know this, why don't we use it? So let's call these two state 1 and 0, okay? And call this system a qubit. And such a qubit is something that could be 1 or 0, or it could be a superposition of the two, okay, with some probabilities, okay? So this is something that goes beyond, okay, the classical logic even, okay? Is this something that is just a complication or is something useful, okay? Well, let's see. Of course, you can now try to identify other systems that can be 1 or 0, so it could be spin that are quite nice because they are looking like vector, and with vectors you do fingers like that all the time. So you can say, okay, pointing up and pointing down, 1 and 0, that's too simple. And then you can put in superposition in many other things, okay? So a good thing for quantum state is this superposition principle, okay? Instead of having the, say, mutually exclusive alternative, what's happening? Sorry, maybe yeah. Yeah, you have such a superposition, which can be depicted in these technical terms with say, Poincare sphere or Bloch sphere or whatever, okay? So let's see first what could be an advantage for this, okay? David Deutsch put forward this idea, okay? Let's take a simple task for computation. We have a single function, okay, that could be constant or a function that essentially swap the value of an input with an input which can be 1 or 0, okay? So a classical bit. Okay? Well, if you want to understand if the function is constant, so it gives all the value all the time, you tried whatever the input or not, okay, you have to try with all the possible input. So if you have two possible input, 1 or 0, you have to try the function, you have to operate the function twice, okay? Well, it shows that if you send a qubit that is properly prepared, okay, so put in the superposition, you can have an answer from the same type of function just using the function once, because you actually put in the superposition 1 and 0, okay, and see the output, and it could say swap it or not, and if it swap it, it's of one type or the other, vice versa. So essentially with this, it proved something that is called quantum parallelism, for which essentially you can simplify the algorithm. The algorithm requires many, say fewer iteration if you have a quantum input, okay? This idea was pushed much further forward. For instance, by Seth Lloyd, he devised a way to implement a quantum computer that does a general calculation, okay? And there are, say, different approaches, okay, to realize such a calculation. So instead of trying as a, say, simple classical computer, so you have a key that open a door, so you have here to try a key after the other, okay? A parallel computer could try all the key, say, in parallel, but you have to replicate, essentially, the stuff, while a quantum computer, using the parallelism, does one single operation, and it tries it all, okay? There are ways using photon, using superconducting qubits, using a magnetic flux, okay, that are, say, possible ways of realizing such a scheme, okay? And we are talking something concrete, because if I'm not wrong, just today, across the street, there should be a meeting on the use of quantum computing in astronomy, okay? Just to put it in a concrete context. Another thing that is good with quantum state is entanglement. Is the fact that you have essentially a correlation. Okay, what is correlation? Well, correlation is something that if I measure something here, I have idea of what is on the other side, okay, or even something similar, like something simple, like I have 3 coins, I put them covered over a table, and I know that at least 2 of them, they have the same face, okay. Well, so this is classical correlation, but it could be extended. For instance, if you consider quantum entities, so these qubits, and you can create with techniques that are already well known and used nowadays, you can create pairs of photons that if they are sharing, for instance, the birth, so they are generating a point at the same time, they actually are described by the same quantum wave function, okay? And they possess a correlation that is more strong than the classical one, okay? To envision this in Schrödinger, say, maximum knowledge of the global properties of a system does not necessarily imply the total knowledge of all these parts, in the sense that essentially the classical example is that if you, again, talk about spin of the photon in this case, and you generate such a pair, you can have that you are collecting the pair, so the 2 photons, okay, in one direction, in the other direction, and the correlation is such that, well, if you just look at one side, okay, well, it appears that the photon has no polarization at all, so every measurement is random, okay? But if you look at both, okay, well, when you see a vertical spin here, you have a horizontal spin there, or vice versa, and it always like this, okay? And one could travel to Mars, okay, and the other one being detected locally, but it's the same, because they are sharing actually the same wave function. So this is another profound, say, change with respect to classical thing. Classically, it would be like this, okay? Say, when you're leaving, use both ends. This is something simply impossible. But on this base, there were protocols that could be realized, like, for instance, the teleportation, quantum teleportation, which teleport a state that is, for instance, produced here, that is measured here, and you are using an entangled pair. You are measuring, essentially, you are projecting the original together with one of the photon of the pair here, okay? And with this procedure, these guys have, say, demonstrated in theory that you actually have teleported this state on this side with a photon that has never met the original one, okay? They never, let's say, cross path together. Okay? So this is the teleportation. This is not just an idea, because it's been, say, a source of experimentation. By the way, Charlie Bennett here is an extremely bright guy and also a very good photographer. He presented me once this photograph of the hole in the water that I have in my room at the university, and I always say ponder with it, because if you are not serious in what you are doing, actually the risk is always facing the hole in the water. Anyway, the teleportation was definitely not one of these, in the sense that it was demonstrated actually on the very same path you have seen before, even on a link on ground of 143 kilometers, and also it was demonstrated by a Chinese team using a satellite that was flying over a location in Tibet. Okay. They teleported a state generated on ground to a satellite. Okay. Well, so you can think of having a border between the classical domain, in which you use a solid planet mass ourselves, okay, and this quantum domain in which you have this superposition principle, the interference of the wave packet, the entanglement, things like that. Okay, and of course it's well guarded by Niels Bohr in person. Okay. And up to that, it was, say, just a division, and it was quite a philosophical issue to, say, wonder what's the actual meaning of the quantum thing, okay? This is a celebrated part of the quantum mechanics history, of the dialogue between Einstein and Bohr themselves, up to a point in which, Einstein put forward the ideas that to him, they had problems of quantum mechanics, so this idea of having some vagueness, some fact that you depend on probabilities, was actually something that was against this idea of having an element of reality, so something that is attached to every observable. If I essentially have something like this bottle, well, I'm pretty sure that this bottle has a position, okay, has a velocity. So it is written somewhere what's the velocity and the position of this bottle in this moment and in the moment that follows. Okay. At the same time, to say contrast the idea of correlation at a distance, so the entanglement, it put forward also the idea of locality. So you cannot have that a measurement done on something at a distance. In relativistic jargon, you call it with an interval type space. You have something that is not, again, I'm pressing a button that I shouldn't press. You have something that influences the measurement here, okay? Well, but this was, of course, answered by Bohr with a very very important paper with the same title, okay, same year, but it was, say, at the level of more or less a philosophical debate until several decades after, where John Bell put a theorem that say, okay, well, if we consider this type of correlation and we take a classical system, then there is a bound on the actual limit of the correlation that you can measure. Okay, so that was a change a very strong change, because it was no longer, let's say, a philosophical position, let's call it, okay, but it was something that you could measure, okay? You say the value of correlation, so like the famous 3 coins, okay? Well, it's something that you can put, again, say, optical tools and measure spins and things like that, okay? And this, started the quest for having an answer, okay? And after about 20 years, okay, a team led by this nice guy with a wonderful mustache, INSPYRE, demonstrated something that was actually related to this inequality of Bell, okay? And what he found was that the type of correlation that was measured in nature, okay, by using real photons, okay, was actually beyond the classical limit. So essentially the result was in agreement with classical mechanical prediction, and so with high statistical accuracy, a strong evidence against the whole class of realistic local theories. Okay, so the position of Einstein was proven to be false. Okay, and this was a big change. Okay, because there was born a whole class of new phenomena. Essentially, a new discipline was born. The quantum information at large was born. Okay, with contribution of many guys. Charlie Bennett, you have seen again, Klaus Jessen, Francesco De Martini, Anton Zeilinger, the great surfer, diver, mountaineer. There's a lot of capacity, also being also a professor in Oxford and Singapore, Arthur Eckert, and for the quantum computing code, we have the smiling face of Peter Shor. Yeah, with a different, say, way of realizing this idea of the superposition principle, the entanglement on quantum parallelism, on communication, and things like that, okay? So in synthesis, just to recap, okay? Quantum technologies, say, took the quantum mechanics that was very essential to interpret the microcosmos, the atom, the molecule, and things like that, okay? This, as a theory, allowed the invention of many things, okay, from lasers to superconductor to transistor, things like that. They are all based on the principle of quantum mechanics, okay? But with quantum information, there was a step forward, okay, in the sense that it was used, the basic element of quantum mechanics were used as tool for a theory of information. So to realize, say, gate that does some algorithm, okay? So they expand the classical concept of the logical bit, okay? So from a theory to understand nature to a tool set for computing, communicate, measure, and so on, okay? Are you with me so far? Any question? Okay, so let's talk practical. So what's the good of this? Take a problem that it's quite widespread and serious nowadays, okay? It's about, I don't know, cryptography, it's about security of communication, privacy, and you may have read a few of these, okay? So when you have, for instance, something that encrypts your card number when you are buying something online, or encrypt the message you are sending over the phone, you need, say, a random key, okay? Well, it was found that the random key was random, but not for all, okay? In some cases, okay, some relevant cases. So there were a flaw on, say, the random number generator, even if they were, say, guaranteed. There was the stamp, okay, of, say, bureau, the bodies that should guarantee the say, generality of usage, okay? And most of the initial information were from actually Snowden, Edward Snowden, okay? that revealed that actually there was, say, a tapping in the phone call of Angela Merkel, for instance, or many other, say, big people that immediately became very upset about this, okay? So immediately the focus was, well, let's look at this random number generator, okay? Well, usually they are generated using a system like this. So you start from a seed, not a natural seed, but a random number. You put into an algorithm, okay, that essentially takes the seed, it does a number of, say, operation, and then after, say, I don't know, you elevate to the power of 10, you do the square root, divided by 1,795, something like that, and then you take the third digit, okay, and you hope that this is actually something random, okay. Oh, it happens that such an algorithm could be actually taped. So, for instance, nowadays, who is developing, for instance, the open source platforms are no longer faithful about these type of things. Okay? These are a few things that essentially report to this. Okay, we have a solution using quantum mechanics because, as we see, when we have, for instance, this transition, you know the probability for such a transition of an atom, but that's all you have. You don't know when exactly a given atom is doing the transition. You have this probability that goes with time, okay? You have a decay, for instance, like even a radioactive decay. But you don't know if that atom that is going to decay is doing it now or later. If you leave it, say, alone, it takes its time, say, to do it, okay? This can also be extended by saying that using quantum mechanics, you can also calculate the amount of randomness, okay, that you can extract. Okay, so how good is the generator? Okay, we are getting into technical detail but this is very important if you want to be faithful on that. So I have to run. If you want to see an example, I brought with you, see the paperback say quantum randomness inside, opening only if you need the ultimate security, and it's this, okay? It's something that has a source. It's actually like here, a laser source in this case, as a beam splitter, and you have the probability for being reflector or transmitter, but you don't know if you are going to be a reflector or transmitter, okay? So what happened here, I'm shedding some light using a classical source. Classical source is not available at the moment. Classical source, by the way, is my phone. Ah, yeah, it is. Let me shoot for a moment this. So you have here the source. Here you have a beam splitter. Okay, so a way in which it goes on one side or the other side. Okay, and then why that has disappeared? Sorry. Okay. And then you have two counters that are suitable for counting counting photons, okay, like before, okay. And these are these two boxes, okay. So the output of these two boxes, so you get a photon, you have an electrical signal. The electrical signal is sent to an Arduino, okay, and the Arduino is just counting them and sent to the computer through here. So now I'll try to show you how it works in reality. So I have to put it there. Okay. So look, I have here the control of the Arduino, and so I've connected the Arduino here, and we are starting, and there we are. Okay, so these are the two lines that represent the counts read on one side and on the other side, say average on a given amount of time, or about half a second. Okay, and so these numbers are varying, and they are varying, and we know the reason why, because these are photons. And for the photons, we have seen already the statistics, the fact that they fluctuate, okay? And we can see such a fluctuation here at the photon counter. Okay? But we can also do something more. So we can say, let's compare the output of such a thing with respect to, so these are the numbers that were generated, okay? And this is the result of an algorithmic, well, it was the first algorithmic computer by IBM, that was called Randu, okay, and well, it seems pretty similar, okay, especially like this, okay. The only point is that if you turn this number, well, this is very simple how to get, in the sense that you have a stream, okay, you divide the stream in block of 8 bits, and you know 8 bits make a byte, okay. That is a number that goes from 0 to 255, okay. Then you take 3 bytes, and such a 3 bytes is a pointing space. Okay? Then you take another 3 bytes, and you plot another pointing space. And you get this or that type of plot. Okay? If you plot for, say, a few thousands point, you get this cloud in the case of the random generator based on quantum process. But if you ask Randu to give the numbers for you, okay, if you look like this, it seems it's quite good, okay? But if you turn it, well, turn, okay? Now it starts to appear something very weird, okay? Well, you have some views for which the numbers are actually aligned on planes, okay? And this is an effect of this algorithmic periodicity, okay? So, of course, if you, say, have a password generator that is based on this, you actually have a much simpler task to do, because, well, you know that you never have a password that falls inside here, for instance, okay? So you have a very strong advantage, okay? So you see, a quantum generator is definitely something that you never can crack that way, because it's based on a measure you do on a, say, a system or a natural system, say the polarization of photons or a decay, okay? And this has happened just in front of your eyes. So if we go back to the presentation, any question about this? Yeah.
So you're showing a quantum system to produce random bits, but what if you take any sensor, like temperature sensor, and you have 30 bits and you read the less significant bits? Would you have something like a quantum?
Well, qualitatively not, in the sense that what you get is something that is the output of a process that you can model. You may reply by saying that the model is very hard, okay? And I'm okay with that, okay? In general, these type of things like cryptography, I mean, I'm not a cryptographer, but the cryptographer, they start all the discussion by saying, what's the level of security you are after, okay? Well, if it has to be on, say, well, my own bank account, there will be not much to talk about, but if you are talking about secrets that, say, a decision that the state have made, and they have communicated to an ambassador, that has to stay secret for the state forever, okay? And there could be consequences for that if it gets revealed, okay? There are examples of people working years in order to crack a cipher, okay? Because there were consequences, strong consequences, possibly the winner of a war, okay? So, is that model good enough? Maybe or maybe not, okay? Anyway, the say, paradigmatic chance is just tossing a coin. They say, okay, it's random, okay? But there were guys at Stanford that took the challenge and make a machine that always land the coin, because it calibrates the movement, the rotation, I think always land head. If you like head, if you like tails, it always land tails, okay? So it's a proof that take a random paradigm and you make it a determinism. So that's the asset, okay? It could be just fine, okay, for many applications, or even super fine for other, okay? The problem is what's at stake. For sure, with a quantum measurement like that, if you have a pretty good state, well, there is no way of knowing it. It's okay? So, let's move on, because we have not seen about moving them away. So, okay, if you want to see the state of the art, we have done recently a big shift of the present limit, which is about 17 gigabits per second. And if you will follow our web in our group, you can also download a gigabit of this level. Okay? Well, another application. Using this superposition, you can create correlation at a distance, which means that I measure something in superposition, and the usual exchange of this qubit is made by a sender that is Alice, and the receiver, which is Bob. Okay, so Alice may prepare state in superposition and know which is such a superposition and send it over to Bob. Okay? And there is a protocol based on quantum measurements that correlate the two parts, which is quite straightforward. We may not have the time to go through the whole stuff, but it's quite simple. Okay, and you can realize this, okay, in order to provide essentially the key that is necessary to again encrypt a message, or to provide that something is the proper, say, author of a paper, or say you want to say that the message is indeed something that has integrity. Okay, so there are a number of applications that again are, say, problems in the information theory that could be addressed by this exchange, and this can be done using, say, a sender and a receiver that even can be not on the same planet, let's say, but one, I don't know, orbiting around, and the other staying on the ground. Okay, there are different orbits, LEO, MEO, GEO, that are different possibilities, because the International Space Station does a rotation every hour and a half, more or less, while the GEO are always there, so you can think of different type of use of these possible things. Why is this returning often to? Okay, and one idea that we study in a project for the European Space Agency is to have a transmitter of photons on a satellite and have the receiver on another satellite, okay? And in this way, you essentially create an inter-satellite link, okay? And for instance, this is the case of the satellite that provides the positioning for Europe, the Galileo constellation, and the blue lines were the two satellites that are closer than 10,000 kilometers, okay? We've done a number of experiments to show, for the first time actually, that you can do this in space, and we all based this type of experiment in a fantastic place that has a special year now, that is Matera. In Matera, besides being the European cultural capital this year, there is also a super important center for space geodesy, where they have this, that is that telescope, 1.5 meter telescope, that has the world record for the accuracy in ranging, okay? And we have worked with that telescope since 2003 to demonstrate actually the feasibility of this quantum communication, okay? And for instance, the first exchange of qubits was proven in 2014 by sending the photon with different direction, okay? Horizontal, vertical, left and right circular, okay? And detecting them in the proper port. Just to show you, this is something that happened at about 1,500 kilometers, but this was, say, extended, and now you have that we can exchange photon up to about 20,000 kilometers, okay? This is the first use we did of the exchange. That was just using it for our motto of the University of Padua. By the way, it was something that was realized by many, say, newspapers and things like that. But the one we liked it most, well, one they liked it most seriously was that it is one of the highlights of 2015 by American Physical Society. But the more laughing one was this, that in Italian, that was taken by a major Italian newspaper that says, "We shall talk with the Martian, and we shall do it in Italian," which was quite funny. Anyway, if you want to see what it looks like, if you stay by the side of the telescope, you just see a beam. I think I have to, yeah, a beam of light that goes toward the satellite. Okay? With that, you can have different also things you can do at the scientific level as a, say, new thing that could extend the knowledge of the space, both on, say, the quantum mechanical side, but also its relation with gravity, okay? And this is something that then can stimulate the interest of younger scientists and students, okay? With this, I think I shall go to the conclusion, okay? And I'll do it by just showing you the thing, okay? As a perspective, okay, we need, I think we are going to close, okay? Is that okay? 1 minute, okay? As a general idea, okay, why can we do this? Well, quantum mechanics has provided this tool to, say, interpret the universe, okay? And set law itself, say the universe is a quantum computer, okay? What such a computer does? Well, it calculates its own future, okay? Continuously elaborate its own future, okay? And actually, said here is in my office, beside a writing in Chinese, which means do good use of light, okay? Which I had written in China. And another perspective is that of Giacomo Mauro D'Ariano, say, events don't take place in space-time, but it's the space-time that emerges from a network of events. Correlation are events, okay? And maybe, in his views, is this, say, exchange of qubits, is this connection that is at the very basic, the essence of space-time. So you have something that are closer if they have more exchange, or more distance if it's the opposite, okay? We have access to the moon, for instance, as a perspective. So there is a lot to do, a lot of work to do actually to understand where we can get there, and to use this quantum communication to longer distance. So you see, in conclusion, quantum technologies in general, they are using quantum mechanics for the theory of information, for the use, okay? So it's different tasks, but at the end we have seen that it can be something that can also improve our understanding of nature itself, so it can work back, okay? And also extend to other disciplines like gravity and relativity. And okay, there are now possible say for instance, a key exchange from a number of platforms. International cooperation in technology application is definitely much needed. In other words, there are new projects, new grants, also thanks to this European initiative, and then position for students. You are in a phase in which you may wonder what to do, and maybe this is an option, okay? And with this, well, this is the photo of a group, actually of 2 years ago, that is in Padua, merging people from physics, astronomy, engineering, some mathematicians also. So a real cool melting pot. We organize meetings and things like that. And thank you for your attention. If you are interested, my references are there. Thank you.
Okay. Thank you very much, Paolo. I don't know if somebody who wants to see the device might come closer to the desk. Are there questions? Oh, I don't see any curiosities or whatever. Somebody wants to ask something? I don't see any. So thank you very much once again. And if somebody wants to see, just come closer.
Yes.